For this example, we have a straight rod which is wrapped around and placed in the inside of this drum. We know the dimensions of the drum, we know the diameter of the rod, we know the Young's modulus for the material, and what we want to do is, if we assume that we have not yet met the yield strength, that is, we're still in the elastic range, what we want to do is find the maximum stress in that coiled rod and what's the maximum bending moment in the rod due to the fact it's coiled inside of that drum. So the picture that we need here, and I'll try to draw the best circle that I can, that this represents the drum. So the center of the drum is there, its radius is d over 2. So on the inside of this is the rod, and so this rod, I won't show it all the way around, but that would have a thickness in there of d, and so if I draw a dashed line which represents the neutral plane of this beam as it's bent, then the radius of curvature, which I'll call rho, we can see from the figure here that rho is equal to d over 2. Subtract away half of the diameter of that rod, so that's small d over 2. We're going to use the equation here that for pure bending, which is what we have when the deflection is purely circular, is the maximum value of y, that is the distance from the neutral plane, divided by rho. And so in this case, y max is just that outer distance there of d over 2. We also know that sigma max is equal to E times the maximum strain. So that's going to be equal to E times d over 2 divided by d minus d over 2 as that. So this just simply becomes the ratio of d times the difference between the two d's, all multiplied by E. So we have all the information that we need, so we've got sigma max. The other fundamental equation that we're going to use is that sigma max, we know, is related back to the bending moment m, the y max, maximum distance from the neutral surface, divided by the second area moment of I. So for a circular cross section, I is pi over 4 d over 2 to the fourth, so this becomes pi over 64 d to the fourth. From this equation, we can solve for the bending moment in that rod, so that's going to be sigma max I divided by y max. So the sigma max, we said, was E times the ratio of d to d minus d. I, we said, was equal to pi over 64 d to the fourth. And y max is equal to small d over 2. So that ends up giving us pi d to the fourth, Young's modulus E, divided by d minus d. So these are the two answers that we were asked to find: the bending moment in that rod, and what's the maximum the maximum normal stress in that rod as it's curved and bent around the inside of that drum. So there are two fundamental equations are really this one and this one here. The maximum strain is the maximum distance from the neutral plane divided by the radius of curvature. In this case, we know the radius of curvature, so it's easy to find the strain. Therefore, sigma equal E times epsilon gives us the maximum stress. The second one is the equation we'll get to know quite well this semester, that the normal stress in bending is equal to my over I, we back out of that, the bending moment M, knowing what the stress segment max is. If you have any questions on this, please let me know, and I'll try to answer your questions.